we studied solar flares, the transition region of a solar flare. So the transition region, this is a small background information. It's the part of the atmosphere between the very hot corona of 1 million Kelvin and the chromospheric plasma of 10,000 Kelvin. And in coronal loops, this section should be some very small area, very thin region of a few hundred kilometers, where you have a balance between the thermal conduction and radiative losses, and perhaps during flares you can also have the enthalpy. And the problem is for many years that the models seems to not are not able to explain the observations in low temperatures below 100,000 Kelvin. The emission is much higher than what it's predicted by the models. And the usual explanation is that you have cool material like spicules or small loops that are crossing the line of sight, and they are covering the emission from the loops. And this is why we try to study this problem during flares, whether even this thin transition region is very bright and with a very high performing instrument like the IRIS. The IRIS instrument. Let me show you some examples. Missing. Yes, here is an example from we studied the emission measure using line intensities that are optically thin, so they are expressed as a square electron density times a contribution function times L is the size of the structure along the line of sight, and you can compute the emission measure from this. It is a square of the electron density times the length of the structure. And when conduction dominates, here you have the simple equation when you have in static loops, where you have the conduction, which is in equilibrium with the radiative cooling and the heating. And in this case, when the conduction dominates, the emission measure should be proportional to the temperature. So these are the emission measure from data observed from a solar flare observed with ICE instrument. And you have the emission measure as a function of the temperature. And you see that the distribution of the emission measure is proportional to the temperature. Now I miss a view graph here, and so I will try perhaps to show you this. Using a. I will make another. Sorry, I will make another save screen on the.
Steve, just to let you know, your presentation has disappeared.
Yes. Do you see it now?
Yes. Thank you.
Okay. So now it's a PDF. It's simpler. Here it is more complete. So here is the complete view graph. So this is the view graph that I show you. These are ICE data, and you have the emission measure that is proportional with the temperature in an older observation of a Skylab area flare. This section of the emission, you have again the emission measure as a function of temperature. And this part of the emission measure is not explained by conduction because it's perhaps a much more powerful flare. And also you have this part of the emission measure which is below a few 100,000 Kelvin, which cannot be explained by the models because you have a much important emission measure than what it can be predicted by conduction. This is an important part of this work, to see if we can understand what is this emission measure. I will present you now the data that were shown also by Spiro Antiochos in the previous talk. This is the flare that was observed. It's a very high flare, an X1.6 class flare. And it is observed by the IRIS instrument. Here you have the slit. It is a spectrograph and also has slit jaw images. These are very good data because they have a high resolution spatial, temporal, and spectral resolution. So Spiro showed you this part of this event. You see here you have the other part of the ribbons are here. Here are the ribbons that where you saw in the previous talk. The magnetogram here. You have the reverse magnetic field lines over there, and here you have also sunspots. Now also another image from the AIA in a plasma emitting at about 1 million Kelvin. Here you have problems with saturation because it's a very bright event, so you have to be careful to take low exposure times to avoid saturation. Here are the images from iris, and you have the ribbons here, which much detail. Here you have the position of the slit. And now I'll show you a combined presentation of the data. Here is the 1,400 emissions. So these are the transition region at about 80,000 Kelvin, the 171, which is at about 1 million Kelvin, and the very hot plasma, which has emission of 10 million Kelvin. Now we wanted to study the foot points of the post-flare loops, and we found that one or two loops are crossing the slit just very close to the foot point. This is not the case for the other loops that you see. You can observe them, but more high in the lengths. We want to be very close to the foot point so that we are sure that in all temperatures we can observe them here. And here you have the spectra. These spectra are calculated along the slit of the iris instrument in different wavelengths. Here you have the silicon 4 line, which is formed at 80,000 Kelvin. You have these sections are loops, and you have a redshift. Here you have the zero velocity is these points, these dots, and you have positive velocities, which mean motions toward the surface. And here you have the iron 21 line, which is formed at 10 million Kelvin and is also observed by AIA here. And here you have the evaporation of the plasma. Here you have the zero reference, and here you have these dots are corresponding to the Doppler shift. And here you have a huge upward motion that can reach up to more than 200 kilometers per second. And so this area here correspond to this part here and this part. And here is the resulting image that I will show you later on. It is the intensity of the iron 21 as a function of the time. Now I will show you in more detail the spectra and the Gaussian fits that we perform. This is the silicon 4 spectral line. And here is the intensity. Now the intensity as a function of time, because iris took sit and stare observations. And you have here you have the position along the slit. And you see here the ribbons. And this part must correspond to the post-flare loops. The Dopplergram, this part that shows you that the bright part of the Dopplergram means that you have redshifts. And here an interesting fact is that between the ribbons you have waves that should correspond to sunspots. You have waves above the sunspots. And another interesting fact is that this spectral line cannot, here you have an individual spectral profile in this area here, in this loop area. The histogram as a data, they cannot be described by a single Gaussian. You need two Gaussians because you have a tail part of the profile in the longest wavelengths that shows you that you have a component that is more redshifted. These profiles, however, when they can be observed along the ribbon, because the ribbon is saturated, you have this component that could be blue shifted. So this is a very interesting physics here. And here you have the Doppler shift, that you have very strong redshifts in this area. Now the other spectral line, this is the iron 21 that is observed during flares. It's a formed at a very high temperature of 10 million Kelvin. You have here an individual profile, the iron 21 here, that is very blue shifted because the rest position of the line is here in this position, but so it is blue shifted. It is very broad because it is very a hot line, and you also have to take care about the chromospheric lines that are blended in. Here you have the intensity, and here you have these loops that I showed you before that are crossing the slit, but this one here must be very close to the foot point. So it is an interesting candidate for a study. And here you have 5 minutes here. Here you have the Doppler shift as a function of time. So you have the evolution of the evaporation flows in a few minutes. And now let me tell you that the problem that this line is a forbidden line. So the contribution function depends on the electron density. So in order to have an estimation of the electron density independent from the line, we computed from the AIA images, we computed the differential emission measure calculation. Here you have the ribbons here. So this is an image of the emission measure derived from this differential emission measure calculation. Here is an example. Here you have the units of the differential emission measure, the temperature in logarithms, and from the integral of this quantity, you can estimate an electron density of 10 to the 11th per cubic centimeter. So this was the estimation of the electron density to compute the contribution function. And now I tell you the emission measure. We computed the ratio of emission measure calculated at the iron 21 over the emission measure of silicon 4 along loops. And the ratio is of the order of 5 to 10, which is much lower than the theoretical emission. As I told you, the emission measure is proportional to the temperature. So here, with the formation temperature of this line, you should expect a ratio of about 100. The same here, we used the AIA 171 images that are formed at 1 million Kelvin. We computed an iris-like image. We performed the same calculation, the ratio of the emission measures of 171 over silicon 4. Here you expect a ratio of about 20 according to this law, and we have a much lower ratio of 0.01, so 0.05. If you go to the ribbon themselves, because there you know that we have flaring loops that are, and the foot points are here in this area for all the cases, and we performed the same calculation. This is difficult because silicon 4 is saturated, and when silicon 4 is not saturated, the iron 21 is very faint. However, here also the ratio is even lower. So the data shows, this is my last slide, the data shows very different results from the theory. The emission measure ratios are lower than the predicted by theory by a factor of 100. You cannot explain that because of cool plasma, because the plasma from the flare is much brighter than the cool speckle-like plasma that could be present there. And so possible reasons that could explain this, these discrepancies could be that we have to take into account the non-equilibrium ionizations of the ions. The ions are in the calculation of the emission measure were considered to be in equilibrium. This is not the case. And perhaps the classic Spitzer thermal conduction doesn't hold. Perhaps because Spitzer thermal conduction supposes that the plasma, the electrons are described by a Maxwellian, or perhaps the gradient of the temperature is of the order of the mean free path of the electrons. There are different considerations that have to be taken into account. Thank you very much. That was my
question. Thanks a lot for keeping in time as well. Very interesting. Any questions for Kostis? Okay, let me ask one question that is practical one and has to do with the feats of the spectral lines. You mentioned that often, and we know that one Gaussian is not sufficient to do it, so you use two Gaussians in order to be able to simulate the skewness, to fit the skewness toward the blue or the red perhaps. But why not using a distribution such a log normal which can account for this kind of uncertainty of asymmetries, or a weighable distribution perhaps, or something like that. That could also align to the physics rather than taking, one Gaussian and another Gaussian and perhaps another Gaussian and put them together.
Yeah, perhaps you typically you assume that the plasma in the low corona is described by a Maxwellian distribution, that the electrons and the ions are Maxwellian. So it's a very obvious choice to use a Gaussian function to describe this profile. Okay, it's also the simplicity of the function. Perhaps in the case of flares, when you could have a non-thermal distribution of particles, maybe we should use another approach. Maybe you're right.
Mm-hmm. Okay, and then another thing. How does this analysis align or non-align or not align, perhaps, with recent radiative transfer kind of simulations that take into account partial or full ionization and give an interpretation of the environment above the low chromosphere all the way to the transition region?
Well, now I studied the spectral lines that I used were coronal and transition region, where you can assume that you are optically thin. So what you said, it's about a radiative transfer. I think this must be more appropriate when you study chromospheric lines, when you study the reaction of the chromosphere to a solar flare. I don't know if you agree.
But you go all the way down to the chromosphere, or you just stay at the transition region?
I'm staying carefully at the transition region. The silicon 4, okay, the silicon 4 line could have problems. Can be optically thick, but not that far optically thick. It's very it can be optically thick, but in a very small measure. You don't have